So in von Richthofen's case, when he went to maneuvering speed in his flying circus aircraft and pulled G's, the top wing would come off because it had too much C-sub-L. So we're going to look at this very simple equation that we've had before. And the simple equation is lift pressure, the lift developed by the wings divided by the wing area divided by dynamic. Lift pressure over dynamic pressure is a number. And we know when this number is a maximum, you're going to stall if you try to go any farther. So the angle of attack for this, somewhere around 16, 17 degrees, and C-sub-L somewhere around 2. Who knows what it is for a particular airplane. But in this case, the top wing had more C-sub-L than the other two wings. So how would I use this equation to predict catastrophe for the Red Baron? All right, so we're going to say the airplane weighs 8,200 pounds. 8,200 pounds, that's the weight of the aircraft. And we're going to say each of the wings is 200 square feet. So I got 200, 200, 200. So the total wing area is going to be 600 square feet for each of 3 wings. And we know the top wing is going to carry, I just said 10% more. Just to show you how you would set up this problem. So if that was the case, and I say that the maximum coefficient of lift right before stall is 2, if you try to get any more than that, you'll stall the airplane. So the angle of attack that gives you CL2, and at 1G, if he's just flying level at 1G, he'll hit a C-sub-L of 2 at 71 feet per second. I'm going to keep the units feet per second because then you don't have to go to the engineering toolbox and convert it to miles an hour. So 71 feet per second at 1G flying level, the airplane will stall. Okay. And the dynamic pressure at stall is going to be 6 pounds per square feet. So at 1G stall, he has 6 pounds coming in. A good test question would be, what is the lift pressure? Well, if C-sub-L is 2, if this is 2 and that's 6, what must the lift pressure be? 12, right? So the lift over wing area must be 12. That's the kind of thing I would ask you on a midterm test or on a final. But we're going to go deeper today. So there's a serious design flaw. When he went to maneuvering speed, if he went to higher speeds, more than he could pull more than 1G, the top wing load was 10% higher than on the other wings. So the top wing here was pulling more lift than these other two, right? When he pulled G's. So the aircraft was rated 4 G's. That meant that the mechanics and the engineers that built this airplane told von Richthofen, you can pull 4 G's on this airplane. When you get to maneuvering speed, you pull 4 G's, but don't pull any more than 4 G's. Don't go any faster and pull more G's, or you'll pull the wings off. Okay, so it's a 4G airplane. So what I ask is, what's the smallest number of G's below that? What's the lowest normal acceleration that would cause the wing loading to exceed 50 pounds per square feet? That's the max. So this wing loading can't be any more than 50 pounds per square foot. So in other words, this here is limited to 50. This guy, that's going to be 50 pounds PSF. If I go more than that on any one of the wings, it'll break. But when I do is 50 PSF, what is my G load? Are the engineers and the builders correct, basically? So what is the smallest number of G's on the aircraft that would cause the wing loading to exceed 50 PSF and damage the top wing or pull it off? It's a hard problem. It's difficult. So I'm going to show you how to set it up, how you might set it up. And I give a hint here. The hint is, we'll solve for the maximum number of G's that produce 50 PSF on the top wing. Because you know, if you're pulling the max 50 PSF on the top wing, then the load on the other two wings is going to be less. So that if I pull any more load, the top wing will fail, but these other two are not going to fail because they have less load. All right. So solve for that G that results in PSF, 50 PSF on the top wing. And 50 PSF on the 200 square foot wing, 50 times 200 is 10,000. So the top wing is going to be pulling 10,000 pounds. If you try to pull any more than 10,000 pounds on the top wing, it'll break. It'll break off. So how would I set that up? Well, I know the wings are equal, and I know that the top wing, we'll call it L1. We'll say this is L1, L2, and L3. The lift on 1, lift on 2, lift on 3. We know that the lift on the top wing is 10% greater than the lift on the second or the third one. Either one, I'll pick the second one. So 10% of the lift on the second plus the second one is going to be the lift on the first one. Or L1 equals 1.1 times L2, or L2 equals L1 divided by 1.1. All those equations are equivalent. That's how I would model the fact that there's more lift on the top wing than on the bottom wing. So you can solve for L2 or L3, and if you divide L1 by 1.1, you get 0.909. So the lift on the second or the third wing is 0.909 times the lift on the first wing. So if the lift on the first wing is 10,000 pounds, what's the lift on the second and third? Well, it's going to be 9,091 pounds. If this is 10,000, 0.90191 times 10,000 will be 9,091 pounds on each of the wings. So the total lift, when the L1 is at max at 10,000 pounds, the total lift being generated by all three wings is going to be 10,000 plus 9,091 plus 9,091, or 28,180 pounds. Notice if all three wings were developing 10,000 pounds, I'd end up with 30,000 pounds of lift. That probably would give me a 4G airplane. But since I'm limited to 28,118 pounds because of the lift on L1, I'm not sure what my maximum G is going to be. I have to solve for it. So my top wing lift is my maximum wing loading, 50 PSF, times 200 square feet, and that's going to be 10,000 pounds. And for each of the other wings, I have 0.9 times, so I'm going to have, what is going to be my wing loading on the other wings? Well, it's going to be 9,091 divided by 200, 9,091. So the wing loading on the other two wings is 45. So when the top wing has L1 is 50, L2 is going to be 45.45, and L3 is going to be 45.45. So the other two wings are still safe when the top wing is at its maximum. Okay. Notice I'm just using a basic, same simple equation that we've used all the way through the class. I'm just kind of showing you how you would apply it to a particular problem. So the total lift for all three wings, 10,000 plus 9,091 plus 9,091, the three wings, L1, L2, L3, 28,182 pounds. And I know that that equals the maximum lift, and the maximum lift is going to be equal to the number of G's times the wing loading, or times the weight. What we have is I've got the maximum lift is going to be NZ times W. I know that's 28,100. So NZ times W. So I'm just going to divide by the weight and figure out what the NZ is. When I do that, when I solve this for NZ, I end up with 3.44. So if the Red Baron pulls 3.44, he's put 10,000 pounds of lift on the top wing. If he pulls any more, if he goes to 4G, what's going to happen? He'll break the airplane. You see that? Okay. Now, what speed is he going when he goes 3.44 Gs? Well, the speed, remember, the speed is going to be buried into Q because Q is equal to 1/2 times the sea level density times the equivalent velocity squared. And this at maximum G is going to be called maneuvering speed. So the velocity that I'm looking for is going to be buried inside of Q. Now let's figure out what the Q is going to be. So here I said, can you show that the maneuvering speed is 140 feet per second? Can you do it? Okay, for 3.44 and CLmax equals 2. Well, you go back to the formula. CLmax is equal to 2. There's the max G's. There's the weight of the aircraft. There's the area of the wings. divided by the dynamic pressure. And notice I just have to solve for Q. I know everything else. Pull your calculator out, solve for Q, you'll get 23.5. Once you get 23.5, you know that that's 0.002377 or 0.00238 slugs per cubic foot. Then you can solve for the velocity. So here's my Q. There's 1/2 density sea level times equivalent velocity squared at 3.44 Gs. Solve for Vman and you'll get 140 feet per second. Or you can convert it to 96 miles an hour. Okay. Don't worry about this over here. I even confused myself with some of the things I asked myself. But that's a hard problem, right? You see, that's a hard problem. So if you can follow me through this problem, then you'll be able to do the quiz today, and be able to do. And you've got a group you can discuss this with, and then I would try to make sure everybody in your group understands what you've done. If not, you can ask me a question.